One thing is that many people who work in the domain, they think like diffusion models are essentially something complicated. I don't think so. I hope that by the end of the chapter you feel the same, because as you're going to see, I mean, once you do it step by step and you do it the right way, it's nothing but doing simple physics. So I guess many people just find it complex because they don't really try to understand the physical aspect of it. They think like it's not machine learning or it's statistical learning, so let's throw it away. But this is I mean, once you think about it from the origin, then it's going to be quite easy to understand. So now let's start with the first part. So in the first part, we are going to just do what we already have done before. Basically, we are going to play around a bit with the Langevin algorithm to just learn how we can generate. And if you remember, I promised you at chapter 3 in section 4 that at some point I'm going to explain you the score matching and score-based models. So today is the time. So we're going to understand that. And this is actually the whole physics of the diffusion model. So back again on square 1. So we are again trying to do modern data generation. So we're dealing with modern models, and these generative models are essentially not obsessed with the data distribution, meaning that they are not going to learn data distribution explicitly. They are looking for a way to be able to sample from the data distribution, right? And they don't care if the data distribution is learned in between or not. And usually, I mean, up to this point, GAN and VAE, you have seen that at the end of the day, you don't have the explicit expression of the data distribution, right? And you don't care, right? Because you can sample from it. That's the only thing you need. So in these modern approaches, so we have some sort of generator, and this generator could be different things. And the whole thing that it does is start from some random process, usually Gaussian, and try to generate the one sample from it, right? And we do a sort of implicit maximum likelihood when we want to train. When we want to just sample, we pass it through the process, right? So up to now, we have learned GAN, and the GAN idea was that you just put this G, this generator, to be a fixed neural network, right? And then you try to make it a way that when Gaussian noise goes in, some sample comes out, and then we ended up having the discriminator, right? So this was the GAN idea. The other one was VAE. VAE was a bit different from GAN. The key difference was that VAE was now probabilistic, right? So it could sample. It was not like a fixed neural network. You just send the Gaussian noise in, and then you get the output. It was a neural network. Gaussian noise goes in, then you can sample from a distribution, right? So you compute some statistic, mean, value, and variance, and then you use it to sample a Gaussian distribution, right? Doing that one, you were able to just show any distribution that you want, but the issue was that, again, you were not able to do direct maximum likelihood because you didn't know the model for the distribution. What did you do? You use variational invariance, right? So these were the two ideas. What we want to do today, we want to make this generator to somehow mimic the idea of diffusion in a physical system, okay? And why we want to do that? Because diffusive models or diffusion eventually start from a random process, which is Brownian motion, and then gradually it's going to converge into a specific distribution. This is from physics literature, not our literature, but this is what we want. So we don't care, we just take whatever works for us, right? So now the whole idea here in the diffusion models is that you want to somehow mimic the idea of diffusion, right? And how you can mimic the idea of diffusion, if you want to really understand this, you need to know a bit of preliminaries, but I promise they are not like complicated preliminaries. You're going to see it, okay? So The whole idea is that we want to mimic what, if, for example, a particle inside a glass of water are going to see, right? So the idea, the one very root idea for it is the idea of Langevin equation. And the name Langevin is quite familiar for you, right? Because we had it for sampling. You're going to see that the sampling that you did is essentially coming out of this equation. So what is the idea of Langevin equation? It tries to explain the diffusion process of a particle. So just a bit of history on this story. So say you have a glass of water, right? And then you just take a very tiny particle, right? A tiny part of, you know, this fur on your clothes, and it just drops in the water. What's going to happen to that guy? Does it go right away down? No, it's going to just jiggle around, right? So how you can explain this jiggling inside the glass of water? This is the idea of diffusion, right? So it was a big physics problem. Langevin has his name here because he tried to explain that. Brownian motion, again, is trying to explain this process. So how we can explain this? There are a bunch of equations, like a super complicated stochastic differential equations are there that can explain this one. But this is one fair model that Langevin had. So the idea here is that I want to know where x is. And x is essentially the location of that particle at particular time t. Okay? So this guy goes inside the water, it starts just go around, right? And then you want to know at particular time t where that guy is. Well, you cannot explain it explicitly, deterministically, because this is quite random. And the randomness comes from all of the, you know, particles inside the water which are hitting that guy, you know, randomly, right? Now, the way that you explain it is this way. You're going to say that this x is the location, and this guy here that you see, I'm writing it down right away, gradient of log of p, because we don't want to discuss physics. We just want to know how we can use it. But for the moment, this whole term that you see here, this gradient term, you can replace all of it with one function f, right? You don't care. This is a function of x, right? So you have this guy here. This is what we call a drift, and t is the time. And b here is the Brownian motion, is the stochastic process, which many of you might have seen is like a limiting case of random walk, right? I'm going to explain it. Now, what does it say? It says that the difference in the location, like when you are at time t, and then you move just with a differential time change, the new location is going to be one drift. This drift factor is a function that you might know it, and then multiplied with the amount of shift in time, that tiny bit of amount shift in time dt, plus square root the tiny amount of change inside the Brownian motion. Okay? So do you see what I don't expect that you understand what is happening inside the equation, but you understand everything inside the equation, right? You understand what the equation is trying to explain, right? So this guy, if you solve it, if you could, this is a differential equation, right? And if you could solve this differential equation, then the xt that you get out of it is going to be the location of that particle inside the glass of water at every single time. And obviously, you see that that guy is, again, a stochastic process. Makes sense, right? So you cannot say where exactly this particle is every single time, but you can say that with high probability is here, with low probability is going to be there, right? You can just say it. And you can say that every single time. Everybody's cool? Okay, so first thing, let me just explain Brownian motion process. Have you ever seen Brownian motion before? You haven't seen it, so you're not interested on stocks, right? So not on economy. So it's very useful in economy. I mean, it's one of the basic things people study in economy. So what is the Brownian motion? It's not a very complicated thing. You start at point 0, right? And at every single time, it just moves Gaussian towards the next time. Just moves Gaussian with a kind of independent process. So if you thought of a tiny, small, quantized time intervals, then every time is just randomly moving any direction that it wants, right? And that is Gaussian. But then when everything goes to the continuous case, those quantizations are just going towards zero. It's a bit harder to define it, but you can define it in this form. So one Brownian motion, it starts at time 0 at the place 0. So when time is 0, it's going to be 0. And then it's going to independently progress through time by Gaussian distribution. And how does that progress impact? It says that if I look at this process at time t2 and t1, then the difference between these two guys is always a Gaussian. Okay? Makes sense. And the variance of this Gaussian is proportional to the time difference, right? So the variance of this guy is proportional to the difference between time t2 and t1, right? So longer time that if you start here, this point is going to randomly go up and down, right? And then the more time passes, the higher the variance would be, right? Does it make sense? Okay, so this is the Brownian motion. It has lots of properties. One key property is that it's not differentiable as you expect, and this is the whole trouble that people need to just develop a new calculus, but this is not the thing that we are going to talk about. One other property is that when you look at like one interval, right? Then the Gaussian process, the Gaussian random variable, which is describing this difference, is going to be independent of any other difference in a time which is not overlapping, right? So if you start from time 0 to time t1, and then from t1 you go to t2, the difference between t2 and t1 is independent of t1 and 0, right? Clear? So this is the Brownian motion, which, as I said, you can think that you start at some point and then Gaussian one. You just at every single time to go to the next time, a tiny bit of change in time, you just decide randomly with zero mean and some variance, right? Everybody's clear? This is how people try to explain how the stock market is just changing, right? This is the easiest model you can think of, right? Because at every single time, when you know this, then the next one is pretty random, right? So in the next opening, it could be just randomly going up or down, right? And this is the way that people try to explain it. Okay, so this is the Brownian motion, and now back to the Langevin equation. So I have this particular equation. I told you this is the difference in time, the location. This is the difference in time. This guy that you see here is drift, and then this is the Brownian motion, right? The difference of the Brownian motion. So I don't know why I don't have the animation here. So these guys should show up right now. Yeah, okay, weird. So now, one key idea here, the only thing that we need to know about this Langevin equation is this particular fact, that if we let x to just go through this process, goes through this dynamics. So you start at time t, you just throw that particle inside the glass of water. It doesn't matter how you send it inside, where you drop it, it doesn't matter. As it passes through time, as it evolves through time, that xt that you have, this xt, the xt at a good long amount of time starts to behave with one specific distribution. Right? At every single time, it's going to be showing the same distribution. And that distribution is actually px, the guy which we have the derivative of its logarithm here. Right? Everybody's clear? So, moral of the story here is that from this equation, it says that if you just start x from any random start point, all right, and then you leave it to just go through this Brownian or this Langevin dynamics, you let the particle to diffuse inside the environment, right? Then if you wait enough amount of time, then at long time from now, if you look at the location of that guy, it's going to be a random thing, and at every single time, it's going to be the same distribution. And that distribution is specified by the drift. Okay? Everybody's clear? You got the idea? Okay, so this is what, as I told you, explaining the diffusion of a particle inside an environment, right? But now, how we can connect it into our generation, right? Data generation or model distribution learning. So it's going to be the best if we look at this guy by a bit of approximation. So we just be a bit naive. We don't think about the real differential equation with dt really going to 0. Let's assume that we can approximate it in a quantized form, okay? Let's do it together. Let's say that I am just progressing in time step by step. It means that I start from time 0, then I just go tiny step forward, delta, right? Then again, a tiny step forward, delta. It's going to be 2 delta, and so on, right? So in general, say that I am at particular time ti, which is t, then the next time that I'm going to be in, it's going to be ti plus 1, which is t plus delta, right? Everybody's cool? So at every single, I am just somehow gridding my time axis. This is the time axis, and I'm gridding it by tiny fractions, by tiny intervals, right? So I'm here at time ti, and then the next guy is ti plus 1, and this difference is a tiny bit. I'm going to show it by delta, right? So that delta doesn't need to be constant. I'm considering here constant, but you just think about a tiny thing, right? It could change even, right? Now, if this is the case, then I can approximate dt by delta, right? I could say dt is roughly delta, right? Then I also had 2 other differentials inside the equation, right? What are they? You remember? What else do I need in this equation to compute what other differences I have? dxt and dB, right? D of the Brownian motion, the difference in the Brownian motion, and the difference in the location, right? So let's do it together. So let's say that I can approximate d of the location to be the location at time ti plus 1, which is essentially t plus delta, minus the location at time ti, which is t, right? So I'm going to look at this time. I see where the location is and where the location is here, and then compute the difference, right? I'm approximating. This is not exact, of course, but if delta is small enough, this is a good approximation, right? Now, this is, I'm going to call, instead of showing this, I'm going to call it xi plus 1. So this is the location at time ti plus 1. And this is xi, right? So the difference between these two locations is going to approximate my dx, right? Same thing for the Brownian motion, right? I'm going to say where the Brownian process is at time ti. It's going to be b of t, and then where it's going to be at time t plus delta, it's going to be b of t plus delta, right? Now, looking at this guy, this delta term, okay, what is the distribution of this guy? Difference of 2 different time instances of a Brownian motion.
The normal distribution with the variance, which is the difference.
Yes, exactly. So look at this Brownian motion again. When you have 2 different time instances, the difference is Gaussian with mean 0 and variance time difference, right? Clear? So what I'm going to just say that this guy is again a Gaussian. Its mean is 0. What is the variance? It's going to be delta, right? So the variance is delta, so it's a Gaussian process with mean 0 and a tiny variance delta, right? Now, I have all differences. I'm going to replace it inside the equation. So what I'm going to do, I'm going to say that dx is essentially this difference, right? This term is the drift. I am computing at time t, which is ti, right? T equals by ti, so I'm computing it at point xi. And then it's going to get multiplied with dt, which is delta for me, right? And then I have the difference, delta b, right? Everybody's clear? So this is approximative form of this same equation, the Langevin equation, right? Now, the next thing that I'm going to do, I'm going to say that this delta b is a Gaussian with with variance delta, right? So can I write it down in this form? Can I say that I have this epsilon, which is 0 mean and unit variance, and then I multiply it with the square root of delta, then it's going to be delta b, right? Yes, because delta b has mean 0 and variance delta. This guy has mean 0 and variance 1, but when multiplied with the square root of delta, it's going to have variance delta, right? So I can replace this delta b with this epsilon times the square root of delta, then that square root of 2 also gets multiplied, and I'm going to replace it in this form, right? Also, I take xi to the other side, and I have this equation, right? Do you remember this equation? Have you ever seen it before? No worries if you have not. I mean, we're going to see it. Okay? Just keep in mind, we're going to go forward and then you see. Okay? Now, this equation that you see is what we call it Langevin dynamics. And what does that mean? That means that if I start from one point, x0, right? And then I initiate a process. This is going to be a Markov chain, right? I have x0, then x0 going to give me x1, right? I put x0 here. This is a drift term. This is a constant term. I can compute it, right? I know this term. This is a random process, right? So I get my first point. I add a deterministic term to it. I add a bias. And then I add a noise term, right? A Gaussian noise. Then I get my new point, right? This new point, again, I'm going to put it inside the equation. I add the next drift. I add the next Gaussian process. And I'm going to get the next point, right? Clear? So x1 goes to x2 and so on. This is going to explain a Markov chain, right? Now, what's going to be the asymptotic distribution in this Markov chain? What's going to happen if I start from any point and then I keep on going forward in time and I wait for enough amount of time? Why it should be Gaussian? No, it's not necessarily Gaussian. Just think about the result of the Langevin equation. Px, great, right? What does Langevin says? It says that when time passes enough, then your process is going to be Px, right? It's going to be with distribution Px. So if you keep on this approximation, if you go on, as long as you have this delta small enough, like you have very tiny steps, then this means that you are approximating the original equation. And this means that in a very, very long time, your x, your location, is going to be distributed by Px, right? Everybody's clear? So this is the main idea. If we just use this dynamics, we can actually sample from the distribution Px, right? I just need to put the Px inside the drift term, right? And then write down the Langevin dynamics, and I keep on going, right? I start from any point, I keep on going. I'm going to have one sample, which is distributed by Px. Everybody's clear? So this is going to be the idea of sampling by the Langevin dynamics. So you're going to start by some x0, one particular time x0, and then you evolve through time. Every single time you are going to compute the new sample, or the new item inside the Markov chain to be the previous one, plus the drift term, plus this term, which is a Gaussian term, which is a variance. And then if you keep going enough amount of time, then finally you are going to converge to Px, right? The distribution. Now, looking at this one, do you remember this? Is it now familiar? Have we done this before? energy models. When we want to sample the energy model, we wanted to come up with one idea of sampling, and one of them was Langevin sampling, right? This is essentially the same thing. If you don't buy my word, just look at this. This is taken exactly from that chapter, right? Look at this guy. So what is it here? So the xt minus 1 is the point which you every time give to your process, right? And then this term, this is the gradient of log of the distribution, which is the drift term, exactly the same drift term. This eta here is 0 mean unit variance, Gaussian. And then you have a square root of epsilon t, right? You only need to write down 2 times delta to be epsilon t. Then this guy is exactly this guy, right? If you just call 2 delta here the epsilon t, then this is going to end up with the same Langevin sampling algorithm that we had. Everybody's clear? Questions? No question? Okay, great. So if you got no question, now I have one question. So if you have this, if you want to really use this idea to generate data, what do you need to know? Do you really need to know px itself? Gradient of log px, right? So if you want to use this idea to generate your sample, again, you don't really need the distribution, right? You don't need to learn the distribution itself. You can just learn the gradient of log of the distribution, right? If you know that guy, then you can put it here inside this equation, and then you can sample from the distribution, right? Okay, so this is the main idea of what we call it score matching or a score-based learning. So what is the main idea? The main idea is that if given this particular Langevin process, which is going to generate samples from our distribution, it seems that it is enough that I just learn the gradient of the logarithm of the distribution, right? I don't really need to know the distribution itself. Why shouldn't I go ahead and learn this guy, right? This is the one which we call the score function. Well, once I have this score function, this gradient, then I can just put it inside the equation. Then that equation is going to mimic the whole diffusion process, starting from a random point. And in the converging point, it's going to be distributed with the distribution that I want. Now, you might ask me, okay, what is the twist here? What is the benefit of just going for this gradient of the logarithm instead of the distribution itself? Well, there are 2 main reasons for that. The first one we already have seen in chapter 3, right? Not chapter 4, yeah. Chapter 3, section 4, I guess. So it's a typo, I guess. Yeah, because chapter 4 was GAN, right? No, it's chapter 3. We have already seen it in chapter 3, I mean, the explicit approaches, when we wanted to just sample from the energy-based model, right? So in the energy-based model, we had this distribution, the Boltzmann distribution, which was exponential divided by partition function. And the whole trouble was to compute that partition function, right? But when we use Langevin algorithm, we could just get rid of that, right? Because the gradient of logarithm of this guy is not going to have any partition function anymore, right? When you take the gradient with respect to the argument x, partition function is going to be fixed in that, in terms of x, and then this is going to disappear, right? So obviously, the thing that you need here is not as, or exactly the same thing as you need when you want to just sample from the distribution or learn the distribution itself, right? So this is one point, but the other point is that once we understand this whole idea, like learning the diffusion process instead of learning the distribution itself, then we can actually, again, come by a trick and then even do that one implicitly. This is the thing that we're going to see in the next section, okay? And then this is going to end up us with the diffusion model, which are again, a kind of implicit models, right? So the second one is still to come, right? But the key point here is that learning this guy is not the same as, I mean, it's not as complex as learning directly the distribution. Questions?